Welcome to Cheenta Statistics and Data Science. Today we are going to solve this problem from IIT GEM MS year 2021, problem number 21. The problem says that let xy be a random vector with joint moment generating function m of t1 comma t2 is equals to 1 by 1 minus t1 plus t2 times 1 minus t2, where t1 lies between the infinities, that means t1 can take any real number, and t2 lies up to minimum of 1 and 1 minus t1. And let z be x plus y, then variance of z is equal to, there are four options. So let us find the variance of z given the joint mgf of xy. Let us do that. So the joint mgf of xy is nothing but this, as it is given, and z is equals to x plus y. So variance of z is actually variance of x plus variance of y plus twice covariance of xy, right? Just using the formula of the variance. Now that means to need then we need to find the variance of x, variance of y, and this term, these three terms, to find the variance of z, right? So let us see this joint mgf. The mgf of x, that means the only mgf of x, we can easily find that by putting t2 equals to 0 in this joint mgf. We know that. So m of t1 comma 0 is 1 minus t1 whole to the minus 1. We can easily see that this is nothing but gamma with parameters 1 and 1. Therefore x, this is the mgf of x by the uniqueness theorem. This x follows gamma distribution with parameters 1 and 1. That means, but if you think what is the distribution of gamma here, what does the pdf look like? But the pdf of gamma distribution with alpha and beta as parameters is nothing but 1 by gamma of alpha into beta to the alpha times x to the alpha minus 1 into e to the minus x by beta. This is the this is the parameter. This is the entire pdf of a gamma distribution with alpha and beta as parameters. So now x follows gamma 1 comma 1. That means just putting alpha equals to 1 here and beta equals to 1 here, we will get the pdf of x. Similarly, we can find the pdf of y, right, just by finding the mgf of y. Now to find the mgf of y, we just need to plug in t1 equals to 0 in the joint mgf. So here t1 equals to 0 and t2 is just usual. This is nothing but 1 minus t2 whole to the minus 2. Again, this by the uniqueness theorem, we can see that y follows gamma with parameters 2 and 1. That means here alpha is 2, alpha here is 2, and beta is 1. This beta, it's 1. This same PDF. So we have actually found out the individual distributions of x and y. But what about the joint? The joint distribution is obviously we don't know, we don't recognize it. Since the joint MGF is not equal to the product of the individual MGFs, therefore x and y are not independent. If had they been independent, the joint MGF would have been the product of the marginal MGFs, but here it is not the case, as you can see. So x and y are dependent, right? So again, but we don't actually need to know the joint distribution explicitly. We are only interested in the expectation of xy, right? Because covariance of xy is nothing but expectation of xy minus expectation of x into expectation of y. So what is the expectation of xy? Is nothing but the mixed partial derivative of the joint MGF with respect to t1 and t2 at the point t1 and t2 both 0. This is the expression for the expectation of xy. It's just partially differentiating the joint MGF with respect to t1 and t2. So just doing that, this is very easy. This is just simple differentiation, partial differentiation, of course, but simple. So here, just first differentiating with respect to t2, this thing we get. Doing the calculations are very simple. Just doing all this stuff, very simple. Remember, when differentiating with respect to t2, t1 is treated as a constant, and whenever we are partially differentiating with respect to t1, t2 is treated as a constant. So you have to keep that in mind. So ultimately, doing this entire thing, this mixed partial derivative is this entire thing. Now we have to actually plug in t1 and t2 both 0. So after plugging in the value, expectation of xy is nothing but this entire thing at the point t1 and t2 both 0 is nothing but 3. This entire thing. If we plug in t1 and t2 both 0, here it's 1 minus 0 into 1 minus 0 is minus 0. So this entire thing is 1. Similarly, here entire thing is 1 into 2 into 1. That means 2. So 1 plus 2 is equal to 3. So this entire expectation of xy is nothing but 3. Now, obviously, since we know the individual distributions of x and y, we can easily find the expectation and variance. We know that for gamma distribution with parameters alpha and beta, the expectation is alpha beta, and the variance is alpha into beta squared. So expectation of x is equals to 1, expectation of y is 2, variance of x is 1, and variance of y is 2. Now, lastly, covariance of xy is nothing but expectation of xy minus expectation of x into expectation of y, right? So it's 3 minus 2 is 1. Therefore, the covariance term is 1. Therefore, we have found out three terms that we needed to find the variance of z. So just plugging in the values, this is 1 plus 2 into 1. This covariance term is 1 as we just found out. So this entire thing turns out to be 5. That means the variance of z is nothing but 5. So the option is, I think, C. C is the correct option, right? So yeah, it's a very simple sum. All you needed to do was just you needed to know how to find the marginal MGFs from the joint MGF, and obviously this term, this was particularly very useful. This was important. This expectation of xy, how to find this thing. Otherwise, you wouldn't have been able to solve this problem, right? So these three terms, three things: how to find the marginal MGFs and this expectation of xy, this as a mixed partial derivative. After that is just pure calculation, very easy calculation. So yeah, there you have it, the solution to this problem. So do like, share, and subscribe to the channel for more exciting problems. See you till next time.